Thanks for coming to the last day of the summer school and workshop. One thing to note, there's been a change to the schedule, so we'll only have 2 tutorials today in the morning session, and then we will break for lunch, and that will be the conclusion of the week. So we end about 12:30 today. Okay, so the first tutorial will be by Dyer, who's at Google Research. He's done a lot of interesting work on scaling models and understanding models' behavior as they scale, both theoretically and empirically. And I think will tell us a bit about both directions. Cool. Thanks, Ethan.
Thanks a lot. Yeah, thanks for the opportunity to speak. And let me say, if anyone wants to interrupt at any point with any kind of question, that's great. So please don't hesitate. Yeah, so today I'm going to be talking about work sort of all orbiting the question of when is scale enough to solve some particular problem of interest. And here I'll be talking about model, compute, and dataset scale. Right, so I'm sure many are familiar with the fact that model performance has just been systematically improving with scale. Here are some, now out of date scaling plots on large language models. So the left is performance versus compute for GPT family models, and the right is similar for Lambda models, which is a Google decoder-only language model. And not only is performance improving on cross entropy, which is maybe nebulous, but if we go and look at downstream tasks we care about, these also often show systematic improvement. So here's a plot aggregating the tasks evaluated in the GPT-3 few-shot paper, and we also see that improvement there is is marching along. And if we could maybe scale up a few more orders of magnitude, at least on these tasks, we would hit broadly human level performance. So the questions that I'd like to focus on are sort of how can we understand this systematic improvement, and what tasks are solved in this way just by scale alone, and what tasks are not. So here's an outline of what I'm hoping to talk about. So first, I'm going to talk about using linear models or kernel methods as a nice toy arena to understand scaling. And then I'll talk about empirical work. First, I'll talk about Big Bench, which is a large language model benchmark that's aimed at probing this question of what kinds of tasks are susceptible to scaling. And then I'll focus on a few different areas. First, I'll focus on how catastrophic forgetting scales, and then I'll talk about some work trying to use scaling to solve quantitative reasoning problems. So, right. So before jumping into empirical studies, I want to review scaling in linear models. This is nice. It's an analytically tractable system that exhibits a lot of the qualitative phenomena we see in deep networks. In some cases, the analogy can be made precise. For instance, if we're talking about very wide networks, or if we're talking about fine tuning, then maybe what we're talking about is literally a linear model. But even aside from that, it can be a useful laboratory to build intuition about scaling laws. And so the setup that I'll try to walk us through is a teacher-student setup where we have some teacher network, capital F, and it's built out of some large, usually, you can think infinite if you want, number of features, capital FM. And then we have a student network, little f, which is built out of some student features, little f mu, and those can just be a random subset of the teacher features. And here, let's see, can I point to things? So here, the subsetting is just being denoted by this projection matrix script P. And we'll draw the teacher weights, just Gaussian, mean 0, and then train the student just with an MSE loss.
Sorry, so what is little f mu?
So little f mu is just some subset of these big, some random subset of these big FM features. So you have some features for your teacher. You just, you have 100 features, you pick 10 of them randomly, and those are your student features. Okay, so this is this is a quadratic problem. We can exactly find the optimum, in the data-rich setting, so many more training data points than student features, it's convenient to write the loss in terms of this kernel, which is just the feature by feature kernel, the features evaluated and averaged over the data distribution. So this is the population feature kernel, and in the large data limit, the loss takes this form, where with this p as the projector from before, and we can ask, how does this get corrected if we're not strictly in the infinite training data set size limit, but in the large but finite data set size limit? And in that case, again, in this whole regime, we can solve this exactly. And what we find is that we can write this not just in terms of this population kernel, but instead we have an empirical kernel like plain C, which is just the empirical average over our training data set size. And this empirical kernel concentrates around the population kernel, and it has higher moments suppressed by powers of 1 over data set size. And so if we ask, well, how does the large, p still less than d, so d is still much larger than the number of student features, but not necessarily infinite, loss scale, we get something which looks like this. We have the infinite data loss piece, L of p, plus a 1 over data set size correction. And the point to emphasize here is just that if we think about how this is scaling with data set size, it's a fixed exponent. In particular, it doesn't depend on particulars of my data distribution. Okay, so we can also ask, though, in this limit, how do we scale when p is large? So here, p is still much less than d, but both are large. And what does the scaling look like at large number of student features? And for this, we actually do need to know something about this kernel that goes in here. Okay, so we need to put in some ansatz that is representative of the data that we'd like to understand the scaling for. And so how do we do that? Well, we can start by just empirically looking at what kernels look like and trying to understand what would be a good ansatz for properties of kernel on realistic data. And so here I'm plotting, in this case, both random feature kernels, but for 2 different setups. So the left is what the kernel looks like if I take uniform random data on a sphere. And the right is what a kernel looks like if I take the same random features, but now on MNIST digits, or take MNIST and pool it at different scales. Okay. And so on the left, we see something where we have highly degenerate eigenvalues, and the degeneracy just grows and grows as we move out in the spectrum. And this is easy to understand. This is coming from the fact that setup, this data is highly symmetric. So if it's uniform on the sphere, this has rotational symmetry, and that rotational symmetry is what's giving this degeneracy in the eigenvalues. And that looks qualitatively quite different from what pooled MNIST or most real data sets that one evaluates kernels on look like. And those look more like a long power law type behavior in the eigenvalues. Yeah.
Some intuition for why pooling causes
yeah. So
could you repeat the question?
yeah, is there some intuition for why larger pooling sizes makes the spectral decay faster?
I meant the.
Oh, can I repeat the question? Yeah. Is there some understanding of why pooling at different sizes makes why does it make the spectral decay faster? Yes, there is some intuition. So one, which I'll talk about in a second. Well, maybe I'll talk about this. So if you're thinking that this scaling comes from some property of smooth functions on a d-dimensional manifold, then larger exponent corresponds to a smaller dimensional manifold. And so if you think that like you're decreasing the data dimension this way, I guess it's not Yeah, so if you think pooling is like sort of removing information and then maybe can be compressed to a smaller dimensional manifold, that might give you some intuition, although you might actually think the data manifold should be the same and compression should be harder. So anyways, I think I don't have a like perfect argument, but okay. So this right. So this kind of behavior motivates an ansatz like this, where the eigenvalues of the kernel follow this power law behavior, where the ith eigenvalue is going like I to the 1 over I to the alpha k plus 1. Okay. So if we make this assumption, then we can actually solve for the scaling of the loss, the test loss with respect to the number of student features exactly. And that can be done either using diagrammatic methods or replica trick. But there's actually a pretty easy way to estimate the scaling if alpha k is large, and it actually gives the same scaling as the exact computation. And so the way to think about that is, here I have some exact kernel script C, and here I have some projection of this kernel onto the student number of features. And if the top eigendirections align between these two things, then there's a cancellation between this and this. So, for instance, if P was the identity, if I had all the features, these two would just exactly cancel and I'd get no loss. So the whole loss is coming from the fact that we're subsetting this kernel down to the student features. And if the way this works is that the top eigendirections align, then those eigenvalues cancel. And so if alpha k is large, then all of the eigenvectors of this projected kernel will approximately align with those of the true kernel. And then we just get only the remaining directions of the true kernel that we have to sum up. And so we get a sum of these eigenvalues up from the number of features beyond the student up to would be S if we have S features, or taking that to infinity up to infinity. And so that gives us this scaling, which is the number of student features to the minus alpha k. And in particular, this exponent depends on the assumption that we made about the data in this mild way, and that we saw different data can lead to different power. And so this scaling depends on the data through that power. So we can rerun this whole story. Instead of being in the data rich limit, we can be in the large model over parameterized limit. And so D is much less than P. And in that case, it's more convenient to write things in terms of this dual data kernel, which is built out of the same features, but now we're averaging over feature space and looking at the kernel on data points. And here K bar is, just like we projected the kernel onto student features, here now we're projecting the data kernel onto the training data set. And again, we find that we have an expansion where the full loss in terms of number of student features and training data set size has this universal term, which scales like 1 over the number of student features, and a data dependent data set size scaling. So just like summarizing this in a simple picture, if we assume some power law scaling for our kernel spectrum, then that gives rise in these different limits to a power law scaling with data set size for overparameterized models, and a power law scaling with model size for underparameterized models, and with the same exponent related to this fundamental scaling of the kernel. But you can ask, can I get some intuition for where that power law of the kernel is coming from? You just looked at some data, I said it looks like this, and this is sort of what I was getting to is there's a few different ways you can get some intuition, but one way comes from thinking about properties of kernels on smooth manifolds. And there's classic work going back to Weil that if I have a smooth kernel with some smoothness condition, for instance, say it's in CT, then I know that my eigenvalues have to be bounded, and they have to be bounded to fall off at least 1 over I to the 1 plus T over D. And so T is this parameter controlling my smoothness, and D is the dimension of the manifold I'm in. So larger exponents, as I vary data, if I want to view that as changing the data manifold, that corresponds to smaller dimensions. And okay, I mean, this bound was true also for that degenerate spectrum that I showed at the beginning, but the extra assumption is that, oh, and yeah, so this goes back to Weil. The extra assumption is that if we don't have any symmetries, if we just have generic smooth functions on this manifold, then what we'll get is something that saturates the bound, whereas these degenerate things subsaturate. Right, and so that then you have a picture here that some smooth generic kernels on d-dimensional manifolds give rise to the spectral scaling of the kernel, and then give rise to the loss scaling in these different limits. Right. So this is another way of summarizing this picture. So here are experiments from random feature models on MNIST, and we have these 4 different regimes. So we call the scaling with respect to data set size in the large data rich regime. That's here, and the scaling with respect to parameter count in the overparameterized regime, that's here. So like to refer to these as variance limited, because that scaling just comes from calculating the variance of how the kernel concentrates around its infinite D or infinite P limit. And there we get these data independent exponents close to 1. And then we have these other regimes, so like the data set size scaling for overparameterized models, or the model set size scaling for data rich models, where we get this data dependent scaling. Okay, so that's great. Fine. Here's some property of linear models. You can ask, well, is this borne out when we look at more realistic models on more interesting data sets? And so this is some experiments on deep models, wide ResNet, and some deep MLPs, a few other models that have qualitatively similar behavior. So here we get these variance limited data independent exponents, and here we get these data dependent non-trivial exponents. And just mapping this onto something that maybe is more familiar, if we look at these 2 panels, in both cases we're varying the number of parameters in our network. And so if you like thinking about double descent, we can ask, okay, we're used to like making plots where we look at loss varying the number of parameters. That's what we're doing here. How does this map onto this double descent picture that I know and love, or maybe feel mixed about? Yeah. So this resolution limited corresponds to the approach to the descent. So we're scaling such that we're pushing this point way to the right, and then we're really focusing on the power law decay to the double descent peak. Whereas this variance limited overparameterized scaling, that's about how do I fall back down to the floor when I'm in an overparameterized model. Maybe one thing to note is that if your currency is compute and you want to get the best model for the least compute, and you're able to change your training data set size or your number of parameters, then the scaling that is more relevant in that scenario is typically this resolution limited, because once I'm overparameterized, I get some performance gains perhaps by making my model bigger, but actually if I just collected more data, that would be and train on that data, that would lead to larger performance gains, given the amount of compute. So, often we're thinking about, CFAR or some setup where the training data set size is like, is just handed to us and we can't change it. And that way, okay, fine, we can get better performance by scaling up. But if you're allowed to tune either knob, it's typically this resolution limited regime, which corresponds to the compute efficient way to improve models. Okay, so just to conclude, so these linear models can exhibit these 4 regimes of scaling that we see, and it requires building in assumptions about the structure of data for that to emerge. And I think this can be extended to a lot of other analyses that are interesting and also relevant for deep models. Studying scaling with respect to compute or time, and can relate to this this deep double descent story. The main thing I want to take away though is just the message that which maybe I'm preaching to the choir, or maybe not, but that linear models I think can still be quite a useful, nice solvable setup where we can build a lot of intuition that carries over to realistic models we care about. Okay. Does anyone have any questions before I move on? Yeah.
I may have missed this connection, but was there a relationship between the rate of decay of the kernel spectra and then the rate of decay of the loss?
Yes. Yeah. So it's differ by 1. So So here this is our kernel spectrum, which is giving us this rate of decay of 1 plus alpha k, and then just doing the sum gives us the scaling with respect to.
Thank you.
So you said that if we had the choice between increasing the number of data or increasing the size of the model, it's better to increase the number of data. But it's not trivial from your theoretical analysis, right? I mean, does the theoretical analysis show that in some way?
So one way to see that from this is it takes it. So we're comparing. Let's just. So it's not complete. I haven't told you what this factor is, but let's just assume it's like some order 1 number, and we can actually compute it. So this decays really quickly, right? It's an exponent of 1, whereas these alpha k's, because they're in this case coming from T over D or just empirically, they're often quite small, and so you quickly exhaust all the benefits you're getting from this, and then at that point. Because you're already in a p much greater than d limit, and so then at that point, because this has fallen so quickly, then gains come from just increasing. Okay, great. Yeah, thanks for the question.
But in terms of the corresponding rate of scaling in the data limited regime.
Say again.
So what determines the corresponding exponent in the regime where you have lots and lots of parameters but limited by data?
Are you asking what is the data set or model size scaling?
The data set scaling in the
limited data.
Yeah.
Yeah, so that is this kernel layout. So the limited thing in the limited regime is always set by the kernel spectrum, and the abundant thing scaling is set by just being 1. So in the data limited regime, your data set scaling is this alpha k, and your model set scaling, this is the over parameterized regime, is just 1 over p, and it flips on the other side of things.
But do we not need to look at the eigencoefficients of the target function?
So in this setup, there is, because the target is built by this teacher, it's all controlled by the kernel. You could say, well, what does that have to do with real data that has a target that I'm trying to learn about? And it seems to be that at least in some analyses, it's really about this data manifold that determines the scaling independent of target. So for instance, you can run an experiment where you train on CFAR 100, okay, but instead of taking the 100 classes, you can superclass them. So you could do, artificial versus natural. That's a 2-class categorization of CFAR 100, or you could do 50 classes or 20 classes. You can dial this and you can ask, does that change my scaling exponent? And it doesn't seem to change the scaling exponent. So I don't have a great, I think this is, again, something we could probably try to understand in linear models. And I think that would be interesting to work through. But it seems like empirically that the changing the input data has more effect on this exponent than keeping the input data the same and changing properties of the labels. Okay, yeah, so now I'm going to shift gears and discuss some empirical work focused on trying to understand what tasks are solved by scale and when we need new ideas. And so one effort in this direction is this Big Bench project. And And so the goal here is to quantify and extrapolate the capabilities of large language models. And so we designed Big Bench as an open call for tasks to the whole research community, and it was organized through GitHub. We evaluated the tasks on large language models at Google, and OpenAI evaluated them on their models, and now also other groups. So Big Science is evaluated on some of their models. DeepMind evaluated some. So the goal is to collect these tasks and then see how their performance improves as a function of the model scales that they're evaluated on. And this is designed with zero-shot and few-shot evaluations in mind, and it's a living benchmark and actively developed. So if you're think there's some great task and you would love to see it evaluated on models, but don't, or want to contribute it or don't want to do the evaluations yourself, like please feel free to submit your task of interest, and we'll evaluate it for you. And so far, this has resulted in over 200 tasks and more than 400 contributors. And okay, you could say like, right, we have a bunch of text benchmarks already. Why do we need a new benchmark? And so one reason is that models are getting quite good, and so that often means that benchmarks are saturated very quickly. So here's a plot from Superglue where we see that like the human baseline was beat within a year of the benchmark coming out. But despite that, models still have glaring holes. So here's an example from Big Bench. If we ask a model, there's an empty fruit basket, then one fig is added, then one plum is added, then one date is added, then one plum is removed, then one fig is removed, which fruits are in the basket? It's happy to tell you that this question would get 71 views, but a related question about how quickly two boys can finish work would actually get over 1,500 views. So maybe you should have been asking that instead. Which is not exactly the answer we're looking for. It's also the hope that if we collect enough tasks and if they're diverse and difficult enough, then it'll take longer to saturate, and also we'll be able to slice these tasks along different axes and maybe figure out which tasks are susceptible to scaling and which tasks are not. And also if we have a broad enough set, maybe that gives us a better way of extrapolating when these capabilities will be or won't be broadly human. Yeah.
So this might be a little side question, but the only case where I've seen that this example here kind of gets quote unquote solved is from like the Instruct GPT work, where they did some reinforcement learning on human feedback to like kind of prevent like these
this kind of thing.
Yeah.
Also, few-shot prompting is quite effective in this kind of thing too. Like here it's like thinking. Well, I don't want to anthropomorphize, but I think in some sense the prompt has not been engineered that much to get it out of the default internet garbage mode and into like questions.
Yeah, because I've noticed that if you just train a really large language model and start asking it questions like this, you just get some like kind of garbage questions like this.
Yes.
I'm curious if so the two main techniques are still kind of prompting and also maybe like some kind of reinforcement learning with human feedback.
Or just fine tuning is also okay. Just even a bit of QA fine tuning, that's enough to get it to. Right. So here are some examples of the types of tasks that we have at the moment. There's a Crash Blossom task, which asks models to identify parts of speech for difficult or ambiguous words within sentences. There's a code line description task, which gives the model a Python code and asks it to guess what the code will do. There's the emoji movie task, which gives the model a sequence of emojis encoding the plot of some movie, and the model is supposed to figure out what movie they're describing. And there's an interactive 20 questions where pairs of models are playing 20 questions with each other, and they win if they're able to correctly communicate the 20 question target. And these tasks can be submitted either as like simple JSON files with lists of questions and answers, or as more complicated programmatic tasks that perhaps require many interactions with the model before scoring. And if we look at how models do, here is aggregate performance for a bunch of Google and OpenAI models, both dense and sparse decoder-only models. And we see that all of these models, generally speaking, are improving with scale. This is over the subset of the JSON task that I mentioned. But we also collected evaluations from human raters. And so we can compare, how the models are doing to those human baselines. And at the moment, they still have a pretty significant way to go to compete with the best human raters. And this score, some of these tasks have different types of metrics. Some are multiple choice, some are exact string match, some are measuring blue, some are measuring rouge. So for each task, submission authors give a low score and a high score, and we can use that to normalize and combine all the scores. And so here, 100 should be thought of as like perfect on all the tasks, and 0 is like random chance or bad on all the tasks. Okay, so like a natural question from this is, okay, this bulk performance is sort of relatively systematically improving, albeit maybe quite slowly. Can we predict performance on particular tasks? And so we can go and look at individual tasks. So for instance, here's a translation task, which asks the model to translate between English and then either rare or constructed languages. And this task, seems to be systematically improving with scale. But then other tasks don't show this kind of improvement. So here is a cause and effect task where a model is asked to determine, what is a cause and what is effect. So for instance, did the child hurt their knee because they started crying, or is it more likely that it was the other way around? And on this task, the model, doesn't really show any improvement. But then, sort of a main confounder to trying to use these to extrapolate capabilities is that there are tasks like this, which seem to show no improvement for many orders of magnitude, and then all of a sudden have some jump in improvement. So this is the emoji movie task, and we see at some critical scale, it turns on, and here, the model is not given any choices, and it just has to pull the name of the movie, out of its memory of reading about movies on the internet. Yep.
How do these numbers compare to the amount of
How does which numbers?
the parameter counts that you're showing us on the x-axis of these plots?
So there's no fine tuning whatsoever on the tasks. This is all few shot evaluations. And so all of these models are trained on roughly the same amount of data. And to the degree that it has overlap with the emoji movie task, that's just because the internet is talking about emojis and talking about movies and stuff like that.
But how does that amount of data compare? For this one, yeah.
Yes. Yeah. This one is happening around, or maybe, it's log scale, so it's like it may be depending on where you want to point it out.
And where it's in for the earlier ones?
For the
previous plot, the previous slide shows other examples.
So like this one where it's just continuing to improve,
Right, and one in between, yeah.
and this one where it's not improving at all. The training data is the same for all of these plots.
Oh, I'm sorry. Okay, I didn't realize that. So these are just the one shot or few shots.
Yes, all of this, everything I'll talk about here, there's no fine tuning. Yeah.
So I can't read the exponents. I'm sorry. So
Yeah, this here,
x-axis.
which says, so the x-axis here, the scales go from about 2 million to about 100 billion parameters.
So it's the right hand.
Yeah.
Thank you.
Yeah. No problem. Yeah. Sorry about that.
Are the prompts tuned for each of the models, or are these just some fixed prompts that were given by the designer?
So the task just has individual questions for these, and we just randomly sample. So here the shot is labeled like none of them, one of them, two of them, or three of them, and evaluate on the ones that were held out.
So for a G shot, you pick 3 random examples.
Yeah, that's right.
Obviously, some of these tasks are like more performance or look how difficult it is to perform?
I think the tasks that are very hard for humans are generally very hard for these models. There are tasks that are easy for humans can also be hard for these models, and then there can be rare exceptions where the model seems to be better than non-expert humans, which the raters have some expertise, but they're definitely non-experts in all of the tasks. So for instance, some of the translation tasks, it seemed like the model was outperforming the raters at this, but these are from there are these linguistic Olympiad problems, and so the model was quite competent at this. I think it doesn't compare to human medalists at these Olympiads, but it seems in this case this was one of the few exceptions where that was sort of not well correlated to the human raters that we had. Okay, so sort of muddying the waters even further, these trends that I'm hoping to see and sort of pointing out, they can strongly depend on things which seem like details that you wouldn't like them to depend on. So for instance, on this cause and effect task, you can rephrase the task so that you actually do see improvement with scale and strong performance. So if you just ask the model, which is more probable, the sentence, the child started crying because the child hurt their knee, or the child hurt their knee because the child started crying, then you see that scale does help with this phrasing of the question.
In the left block, does the model see both the answers before it has to do anything?
It's so the way these multiple choices are evaluated is it looks at the probability of these two, and then asks which is more probable. So it's prompted with this question and then answer this one. That gives that full sequence some probability. It's asked, question and then answer this one. It gives that sentence some probability, and then whichever probability is higher, that's taken as the model's answer, and then that's scored. Does that make sense?
Yeah, that explanation makes sense, but I don't understand why it makes sense given the input prompt that the model is given beforehand, because it isn't. Wouldn't you expect it to somehow see both of these and have to
So we've evaluated in two ways. One where you say choices, and then it shows both in the prompt, and then you do this, and where you don't. That can actually have a big effect, and actually it can often be the case that, well, it can be the case that it does better without showing the choices, which, yeah, I mean, I think that's not what you'd expect, right? You'd expect the choices to just help, but maybe you think it's getting distracted by having extra tokens in the prompt or something like that, or being pushed out of distribution. So okay, so here, just rephrasing this way can change the trend. Also, the degree of regularity across tasks can depend on how we grade them. So here's an emoji movie task. If we do this exact string match where it has to pull the name out of the blue, we see this discontinuity. If we give it multiple choice questions, in this case also without showing it the options, it seems more systematic. And these things can also depend not just on how we phrase the question, but how we score it. So, if we're looking at multiple choice grades, sometimes we see these jumps. If we're looking at what's the probability that the model assigns to the correct answer, that can often look smooth. And there's also phenomena where it seems like the model might not be learning much, it might be learning really slowly. Yeah.
Can you go back to the previous?
Yep.
What was the multiple choice versus?
So here, these are mostly multiple choice accuracies. So does it select the correct, it's comparing now a probability of correct answer to probabilities of wrong answers. And so to get it right, it has to have the right answer probability has to be higher than the wrong answers. Whereas here, it's just what's the probability of the right answer. So a cross entropy type loss for this. And that's smooth. So it's just continuing to assign better and better probability to the right answer, but that only beats the wrong answers here.
So similar to like the grokking paper, it had like this logarithmic x-axis, and I saw one criticism of it is like you should make it a linear x-axis. It actually looks quite smooth because like the difference between 10 to the 10 and 10 to the 11 is quite a bit of numbers.
Yeah.
Do you have any just comment on like the appropriateness of using like a logarithmic x-axis for setting these like and calling them discontinuities?
Yeah. I think like if I wanted to be diplomatic, I think definitely jury's still out about discontinuity. I mean, some of these look quite dramatic even on a linear axis, but this can skew things. But I think like experiments like this are sort of first attempts at trying to understand, is there actually some fundamental discontinuity going on or something smooth? I mean, I think it's good to plot it in both ways. And I think like for me, I think like whether there's a real phase transition that's underlying this, I haven't talked about some like models, speculative models after, but the jury's still out. Just briefly, and maybe related to attempts to understand that, you can ask like, even for tasks which seem like they're not showing much improvement. So here's a task where the model is asked to it's given a series of moves leading a chessboard to some state, and then there should be one checkmating move after it. And the model's asked, given that the whole game in context, can it find the checkmate? So that's the task. And you can look, how is the model doing at finding checkmates? And that's this red line here. It's not doing great. It's worse than if it, then you can ask, well, actually, sometimes it finds checkmates. It just doesn't use chess notation. It forgets to put the pound sign before its checkmate. So this pink line is if you just find it, like let's just be happy to found checkmate. So still not a huge improvement, but you can just ask, okay, what kind of moves is it making? And it's actually making more and more legal moves. So to some degree, maybe the model isn't learning checkmates at a rate that we're happy with, but it actually is getting pretty good at making legal chess moves in this setting.
When you evaluate these models, are you evaluating the top answer or are you evaluating the top 100? What exactly?
This is it's the top answer, yeah. But yeah.
Do you think that's right? Like, do you think that's what we should be doing? And maybe we should be doing majority vote on top.
Yeah, I'll talk about other inference techniques in a bit, but I think these are all good ideas, and like we can maybe put this into what we call the model, but then think about how do we change things to improve on this naive? Yeah, definitely there are smarter things you can do than this. Okay, so right, so in conclusion, Big Bench is this large benchmark. One thing that I found nice about it is like I'm maybe interested in some topic, not thinking about Big Bench, and then I'll realize, oh, actually there's like a related task already in Big Bench. If I want to know how it scales, I can just like pull up the plot that's already been computed and see like, does that task get better with scale or not? So like perhaps if you're interested in something, maybe there's a related task already there that like you can get, use to build some intuition. If there's not a task there and you'd like to know, please submit. And I think, understanding this breakthrough behavior is very important for our ability to like extrapolate capabilities. And also I think is like a rich target for theoretical analysis. And also, we see here lots of tasks which are systematically improving, but at a rate which is totally infeasible to think about using this as the approach to solving. So, just something, getting better with scale doesn't necessarily mean that scale is like the answer to solving this problem. Okay, great. So now I wanted to move on to a couple of focus problems. And the first one I wanted to talk about, the role scale plays in catastrophic forgetting. Yeah.
Can scaling language models help with limiting hallucination?
Limiting hallucination? That's a good question. I actually don't know off the top of my head of results on that, but I think that's
okay.
Great question.
I think there was one paper that claimed that it does.
Oh, okay.
Cool. Yeah. So what's the typical catastrophic forgetting setup? The typical setup is that we sequentially train on two tasks. So for instance, say we want first to classify muffins versus chihuahuas. We train a model to do that, and then we subsequently train on classifying fried chicken versus poodles. And once we're training on the chicken versus poodle task, the chihuahua versus muffin task performance would typically drop. So that's the usual forgetting setup. And maybe it's interesting on its own right. I think the real reason we care about this is we think it's a good probe of a more general phenomena, which is just that if we have distribution shift during training, then often that can interfere with models' performance on previous tasks. And why might we think that scale might be helpful for this? So one piece of intuition comes from thinking about language models again, which is that here's the example of another task from Big Bench, which is just asking a model to match the atomic number to an element. So this is like a recall task, and large models are quite good at this. But presumably, whatever data it used to learn that, this data set it trained on is huge. So presumably that was many gradient steps back, in training between when that appeared and when this model was evaluated on it. And yet it's still able to do very well at this in this few shot setting. So this leads one to believe that it can retain information. These big models can retain information from any gradient updates. And so sort of in that spirit, we decided to pre-train some big models on ImageNet 21K, and then study how forgetting was dependent on the scale of pre-training data and model size. And the way I'll mostly be plotting things, just to orient people, is on this 2D task A versus task B plot, and I'll sometimes refer to the forgetting frontier. And the point is, if we think about, we've trained on task A, and now we're training on task B, we start out with some good task A performance, and then as we train longer on task B, our task B performance gets better and our task A performance gets worse. And so models that forget less are models that are moved further up and to the right on this plot. Great. And so so we can look at how do these big pre-trained models do on forgetting tasks. And so here are some vision transformers and ResNets, and we see that we get quite dramatic improvements in forgetting. So this is just taking the best average accuracy that we can get, so choosing the optimal stopping time in that way for these models, and we get these this improvement with scale. Okay, but this raises some questions. You might say oh, well, is it just about the model size? So one way to get at that is instead of doing this pre-training, we can just train models from scratch on the first subset, and then ask how do they do on when we do task pre-training. And we see that really to take advantage of this scaling, it's not enough to just have bigger models. We also have to have scaled up our pre-training data set size. You could say okay, fine, but pre-training and bigger models that improves accuracy. Maybe it's just about accuracy that we get. Maybe if your task A accuracy is just good enough, then you don't forget that much. So here is some experiments where we handicap the task A training of the pre-trained models so that its performance matches what we get from a trained from scratch model on this task A task. And we still see that pre-training and scale confer benefits even when we're matching original task accuracy. Another question, which I think actually understanding this deeply is interesting question, is that to what degree does the overlap between the tasks you're doing your forgetting study in and this pre-training data that you trained on, what's the importance of the overlap between those? I think my naive guess was that if you have a big diverse pre-training data set and your next tasks are sort of within it, that's sort of a good recipe for mitigating forgetting. And that's great. It still presents an approach, and you can maybe have a big unsupervised pre-training data set size and then have supervised tasks. But it turned out that actually this behavior maybe requires us to rethink what we mean by in and out of distribution, or extended further out of distribution than I expected. So here's some experiments on a variety of fine-tuning tasks, and in particular, we saw pretty good behavior on SVHN forgetting and domain net clip art forgetting, and ImageNet has no numbers in it, and it has no clip art in it, and so maybe that's fine, and we shouldn't think of those as being out of distribution, but at least like some naive guess of where I might expect to see this breakdown didn't happen. Okay, so yeah.
How much data were in task A and task B? How big are those tasks?
Yeah, so that was, so for each of those, it's like whichever task is there, it's split. So like for the CFAR 10, it's like 5 classes and then 5 classes of CFAR.
Do you think like the scaling is possibly just like deferring the problem? Like if you scale the task up while you scale the model,
I think that's quite likely that if you make it big enough that let me say this in a way that I actually believe. So I think if you just kept like these CFAR splits and just took more IIG samples from that, I don't expect there to be a significant problem. But if you like started adding more and more tasks that it had to keep, and it was supposed to keep remembering all of them, so we did this for 10 different splits, but still like my guess is that there's some amount of continual learning that like will compete. Like there's some way in which you need to scale the amount of continual learning with your amount of like pre-training and model scale to take advantage of this. So like at some point, like if you have enough data, you'll sort of wipe out the be enough to saturate the capacity of your model, and then you won't get this kind of improvement is my guess. I think it would be interesting to understand like how those two scale together.
so you're saying that for the bigger model, if you fix the same 2 tasks and you scale up those 2 tasks, it should do fine. But if you increase the number of tasks itself, then it might start to.
Yeah, I suspect that's happy to speculate more after too.
Any insights from linear models for catastrophic forgetting?
Yeah, there are some actually. So one feature of like these forgetting is that it often happens in the last layer of the network. So if that's true, you can model this quite well because now you have some pre-trained features and you're training a linear model on top of those pre-trained features. Because if it was true that it was literally in the last layer of your network, then you would just have some frozen features multiplied by some linear weights. And so one thing you can learn there is like, you might ask, if I'm training on task A and task B, how does the similarity between those 2 tasks affect the amount of forgetting? And what you find is if the tasks are very similar, like IID data from the same task, of course you have no forgetting. If the tasks are very different, you also have very little forgetting. So if those linear features are like orthogonal, then they don't interfere and you have very little forgetting. And that it's actually this intermediate similarity that leads to maximal forgetting, and you can derive this behavior in this frozen feature linear models setting. And so that's also another motivation for scaling up is, maybe with no training, I can't recognize that like this subset of CFAR and this subset of CFAR are actually like pretty orthogonal. But if I had a huge model that's pre-trained, now it like even without these labels, it's great at having features that represent cats and dogs differently than planes and trucks. Like those have very little overlap. And so if low overlap is a recipe for getting low forgetting, that's sort of part of another motivation of why you might think like large scale pre-training is helpful for getting low forgetting.
What's a good metric for measuring how similar 2 tasks are?
Yeah, that's I think a good question in general. Here in that frozen model, you can look at the overlap between these features. So in this model where it is just the last layer, like you can use that as a proxy, even in the case where you're training the whole thing. And that seems to correlate quite well in this case. Okay, so in just a couple of remaining minutes, I wanted to move on to this question of like, quantitative reasoning. Something that at Blueshift we're quite interested in is like, how can we get models, to be better scientists? How can we have them do quantitative reasoning? And so then a natural question we like to ask is like, okay, to what degree is scale helpful in this? And so, in general, we want like general purpose, quantitative reasoners. I'll often be focusing sort of on a toy window into that, which is, science and math question answering type problems. And, many have speculated that like we need scale is not going to be that helpful with this. Maybe we need symbolic logic or, something else that we're missing for these kind of, maybe quantitative reasoning is different than language model. And so to try to investigate this directly, we trained a big model on, unsupervised but math-heavy data set, and just try to see what we could get in terms of quantitative reasoning skills. And so the ingredients are math-heavy data set, a large pre-trained model, pre-trained on general text, and then further unsupervised fine-tuning or additional pre-training, if you want to call that, on a data set that contains a lot of math, and then some inference time techniques, which I'll walk through in a second. Right. So the key to the data set was just making sure that it wasn't over cleaned. So some naive cleaners will destroy mathematical notation, like you have A over B, and that just becomes A space B. Or in this example, you have E equals MC squared, and the cleaner just changes it to EMC2. And so it's hard to imagine that if you're ruining the logic in the data, the model will learn any logic. And so we took POM, which is an existing internal big pre-trained model, and then further trained it on this, not over cleaned scrape of archive and web pages that had math jacks on them. Yep.
And the unsupervised fine tuning is predicting
next token. Yeah, same. Yeah, exactly. Okay, and then we evaluated it, and to evaluate it, we used a few techniques which have become popular. So one is called chain of thought or scratch pad, and so the typical few shot, you prompt with question, answer, question. Here, instead, you prompt with question, justification, answer, question, and that encourages the model, as it's answering the question, to spit out some justification, which hopefully it can use that justification to reason about its answer before spitting out the answer. And also it lets us investigate, a perhaps flawed window into how the model's coming to an answer. And then we also did majority voting, which means we don't just take one most likely answer. The model generates a bunch of answers. So here it generates a bunch of reasoning steps and a bunch of final answers. So, maybe it'll come to, the answer 5 3 times and the answer 2 1 time. Those 5s will have different ways it got there, but there's more 5s. So before grading it, we let it take the majority vote over these samples, and that's what's used as the final answer. Okay, and so, with that, you get quite, quite big improvement on performance on a lot of math and science data sets. So there's this Hendrix math data set, which is asking high school level, but contest problems across a variety of math domains. There's MMLU STEM, which is asking questions over a variety of STEM subjects. We also evaluated on various high school, undergraduate, and graduate course questions. And the model does learn at least is able to imitate in some examples, reasoning quite well and quite better than previous models were able to. And I think so. I know I should wrap, but just to I don't know. I find it fun to inspect. Oh, I have 15 more minutes. Oh, all right, great. So I can talk in a pace that people can actually understand. Yeah. So, anyways, it's fun to, I find it fun to inspect and anthropomorphize. This model solving certain problems. So here's an example where it's asked to figure out the velocity, the speed for a model for a particle moving on a circle, and it's able to take the derivative and then compute the magnitude of the vector and then spit out the answer. One fun thing is so this model is trained in this unsupervised fashion on all the data we could scrape that had tech in it. And so a lot of that data, the tech is importing some drawing package and then drawing something and making some statement about the thing that it drew. And so that means, out of the box, the model is able to do some reasoning about questions with diagrams. So here I'm drawing it in a way which I find easier to see where it actually has the diagram. Of course, what the model's seeing is just the tech package that draws the diagram. So this one's asymptote, which I didn't know until seeing the model spit out asymptote a bunch, but I guess is a popular drawing package. You can also do this for TIC-Z or other things like that. And what I like about this example is so it's asked to compute the area of these gray regions. And the way I would have solved it is I would have computed the rectangle and then subtracted the pink triangle. And the questions in math come with a reference answer, which the model hasn't seen, but that's also how the reference answer does it. The way the model decided to do it was that it recognized that these were both triangles themselves. And so it separately computed the area of those two triangles and then added them together. Anyways, which, is totally fine. And maybe that's, I don't know what other people's like default would be, but it tickled that the model is doing it differently than what I thought would be like the easiest, the naive way.
Could that be because that's how it's coded up? Like there's like two positive triangles instead of one negative triangle in the.
Good question. Yeah, that's worth looking at. I like another anecdote along those lines is sometimes I was like, oh, this model solving this problem is like it's doing it like instantly. Like it's asked to get the area of a region, and it's just like, well, the length is this and the width is this, so the area is that. Like why, you're supposed to reason about like, so okay, the concrete example is you have a rectangle divided up into 4 subrectangles. You're given the area of 3, and you're asked for the area of a 4th. Okay. And the model was just saying, oh, it's the 4th area, like the length is this, the width is this, so the area is that. And it's like, well, how did you know that? You must have memorized the training data. At this point, like, very nervous about memorization and stuff. So, okay. Then you look at the code and they've like hard coded in the size of each of these things, so you don't see this when you're, but so, okay. So, yeah, so, and if you change the numbers, the model is able to change with, so, I think it is just cheating by looking at the code, not cheating by memorizing the internet. The model also definitely has its fair share of failure modes. So some examples are false positives. Those are sort of, the most difficult because it makes you question the score you're getting, and it also, if you want to use its samples to like do further training or something like that, it would be nice if you could weed out false positives. So here's an example where the question asks you to continue this pattern and ask if you continued it, what would the 30th number be? And the way the model approaches it is it thinks the pattern continues by just having all the remaining lines have 5 numbers in them. So like 5 6s, 5 7s, 5 8s. But in this case, that like gives you the same thing as doing it correctly. And so, the model clearly has the wrong logic here, but the problem isn't sharp enough to distinguish that. There are other examples, many examples that it just gets wrong. Here's a cherry-picked one where it's asked to solve this equation, and it decides that we can just cancel the square root, and then it uses that to try to solve the equation, which would be great, but unfortunately, there's such thing. Okay, so right, so yeah, I wanted to conclude, and then maybe have time for questions. I have more examples if people are curious to see, but so right, so definitely, it's not at all clear that scale is enough to solve most or all of the questions we care about, but I definitely think it continues to be a option that is worth trying, even like it sort of, at least for me, like it's often surprising what you can get from scaling things up without much many clever ideas. And I think it's a useful null model to rate other things against. I think from a theory perspective, some things follow like very robust, predictable trends. And so that's just sort of, sometimes independent of details of architecture, sometimes independent of details of data. And that's the kind of thing that just begs for theoretical understanding. And then there's also this counterpoint that there are other things we definitely don't understand when trying to predict performance on particular tasks. And if there's a goal of trying to extrapolate, predict performance or understand what's going there, I think that's also a very important target. And then sort of going back to this null model perspective, if we're thinking about things like hallucinations or, architectural modifications, it's often useful, at least for me, to say like, well, okay, how do I compare to doing nothing? Like, if I change some detail of my architecture and I, get some maybe better performance at some scale, like, does it change the scaling exponent? Does it change the prefactor? Like, maybe maybe you're still excited if it doesn't, or, or maybe prefactors can be very important, but at least as a method for organizing how to think about different types of research, I think it's quite useful lens. So, Yeah, with that, I guess I'll close and just say thanks for letting me speak.
So we have about 5 minutes for the remaining questions.
Examples at the end, you're using an ensemble and choosing a majority, I guess, of the answer.
So the way that this the grading works. So for the performance plots, yeah, we would generate 256 examples, and then we would say that each example has its own reasoning and then its own final answer. So we would aggregate over the final answer, and we would ask how many had that, and we use that. In the cherry pick samples, you just picked like the first or random one from the 256 to show.
Right. Okay. And I'm curious. So I guess the randomness that's there is the randomness that's used to generate these things.
That's right. It's some temperature. We use temperature 0.8, I think, for this.
And I'm curious, what's for those sorts of examples? What's the variation that you see between them? Is it variation of reasoning, or is it?
Yeah. That's a great question. There's some reasoning variation. There's also like just phrase like style variations. For the ease, so these problems, in addition to having categories, they're also graded like in the math problems, for instance, which are the ones spent the most time inspecting. They're also graded by level. So there'll be like algebra 1, algebra 2, algebra 3, not just algebra. So for the simpler problems, we often found much less variation in the way the model is answering it. And like if the answer is short, also a lot less variation. And then as the problems got harder, you would typically see, a bit more variety in how the model answered. I think these kind of questions are interesting, and also I think a standard thing that is always very useful and often like more useful than being clever is also ensembling models. And so definitely thinking about can we promote even more diversity in how it's answering these and stuff like that. So.
Yeah, so I'm trying to consolidate what you were mentioning here about Minerva with another recent paper of yours, which was on length generalization. And I'm curious how you think about the two in conjunction, where you have the length generalization results showing horrible model performance on out of distribution stuff. And then, so does that kind of imply that Minerva's abilities to do what it's doing are kind of suggesting that somehow the number of decision steps required for these tasks are in distribution compared to what you trained it on?
I think that's right. Yeah. I think again with harder tasks, one of the ways it can fail is maybe reasoning through an answer requires 20 steps, not 3 steps, and then it can have a mistake at some intermediate point. I think even there are techniques to try to you can take a problem. With some of this prompting, sometimes the problem can stay the same, but by cleverly prompting, you sort of can make it a distribution problem rather than an out of distribution problem. So for instance, long addition is a thing which people say, oh, these models are very bad at length generalization of long addition. And that's definitely true. And lots of ways you prompt them, they are bad at it. But it turns out there are some ways of engineering a prompt or asking it differently where these kind of questions are more in distribution. And then anyway, so I mean, I think that's not a solution. You'd really like some robust procedure that let you generalize beyond that and not just sort of hackily try things and see what works. So anyway, short answer is yes. I think basically it's not inconsistent, and it's just that there's enough 0 to 10 step type things in the training data that's can be emulated here. I think understanding how that fails would be good, but yeah, I think to get long form reasoning probably requires more than just
scale.
Yeah.
Thank you.
Maybe one more question. Yeah.
So you started the talk of talking about kernels, and you went on to transformers, which feels super different.
Yeah.
Is your intuition for why you sort of the reason why you were able to construct power law scaling for kernels? Mm-hmm. Is there anything that you see carrying over into the transformer setting, or is it just they both sort of have to happen?
Yeah, that's a great question. And I'll give an answer which I think is maybe very optimistic and could easily be criticized by someone who wants me to be formal. There's another approach to getting these kind of scaling laws where you don't assume some particular model structure at all. You just the key assumption is like smooth functions on smooth-ish, and probably that can be weakened to data manifold. And then there are results that are like classic results in the literature that, if I'm, sometimes they're phrased as mesh interpolation results. So like if I'm trying to approximate a smooth manifold with a mesh with some number of vertices, how does my error scale with the number of vertices? Sometimes they're phrased as nearest neighbor. It's really a nearest neighbor question, because as I scale up my number of vertices, or as I scale up my training data set size, the distance to my nearest neighbor scales like a power law, but that power is controlled by 1 over the dimension of the manifold. Nearest neighbors are further if the dimension is bigger, but as I add more data, the nearest neighbors get closer. So that kind of perspective also is what's underlying the linear story. If you believe this like smooth kernel, like the smoothness on a d-dimensional data manifold is what's driving it. But that can be generalized. It just needs smoothness. It doesn't need some particular architecture assumption. I don't know that that's literally what's happening, but that at least seems like a route to some general story that connects these things.
Do you have intuition for what smoothness in language, like with respect to natural language means?
So the way I think that's a great question. The way I usually think about this is in embedding space for all this stuff. So when I'm talking about like nearest neighbors, I'm talking about like the model's representation of data. And so there it is more like, there it is like smoothness, like actual smoothness on the representation.
Thank you, Ethan, again. And we now have about a half an hour break. We'll be back for the next tutorial at 11:15.
In the prompt, you mean? Yeah. Yeah. So it's 4 examples in the prompt, and then it's asked a bit question.
Yeah. So
Right.
So is there a way that the actually make sure that for example, even children when you want
Questions on that?